on DuckDuckGo or Google. We're going to do a talk about time and synchronization. Initially, in your schedules, I said like, "Ooh, we're going to do an overview of all time and synchronization in GStreamer." Unfortunately, I realized very quickly I would need a 4-hour slot. So took a few steps back and decided, what is the real intent of this talk? This talk is, and I realized that a lot of people are confused about when we start talking about running time, clocks, stream times, latency. So we're going to concentrate on really understanding what the basics of timing and synchronization in GStreamer are, why they are made like this, why we do them like this in GStreamer, and how. And we're going to start with simple examples. So it all starts with time. What is time? That was a tricky one. Went to Wikipedia. Thank Wikipedia. So time is the concept by which we can order events. It happened in the past, it's happening now, it's happening in the future. But I gotta say, it's tricky because it's something that you can measure, but you can't. I mean, give me, what is the time? There isn't a time. We're going to determine time based on measuring durations of events or interval between events. The one good definition of time, and I like this, is that a certain number of repetitions of one or other standard cyclical event constitutes one standard unit of time. In this case, a second. It could also be a day. It could be a year. It could be a millisecond, a nanosecond. So time is essentially that. It's we're going to have some repeating events, and then based on that, we're going to establish, oh, these are one day has gone past, or this represents one day, and then maybe we can divide it to determine other units, durations. So we can't determine, we don't have an absolute value of time, but on the other hand, we can measure time. We're going to measure time with chronometers or clocks. The clocks are slightly different. Very quick history. First measurement of time before Christ is essentially when the first cyclical event that we all know is days. Every day the sun comes up. If we were to put a stick in the ground and look at the shade and put a marker, and we wait for it to come back, that will be 1 unit. It'll be what we now know as 24 hours. That's how people started measuring time. Very basic. But then afterwards, they were like, yeah, this is great, except that sundials don't work during the night. Or in Scotland during the day. Anyway, they were like, we need to find a better system to calculate time. So, and I think the oldest example is in ancient Egypt, where they went, well, so wait a minute, if we take water passing through a specific hole, that flow is going to be constant. If we remember the definition from before, it's a cyclical event. So the flow of water is constant, and if we look at how fast water goes down, well, we can start putting measures. Going like, that's 1 unit of time has gone by. So what I did is essentially take those big water tanks based on the sundial. So they're referencing another unit, like I say, chronometer, and then went, okay, this much water goes past in 1 day, and then started dividing it, and at night they were able to see the passing of time. Then afterwards, let's carry on. I mean, hourglass is the same concept as a clepsydra, as a water clock, except that it's using sand. Very useful. Magellan had 18 hourglasses in his boat when he went around the world, so he was able to know how much time has gone by since he left Lisboa or whatever, and candles. So once again, you've got a system by which you can measure the passing of time, but based on a reference. So the hourglasses were calibrated such as a full hourglass empties in 1 hour, for example, or 24 hours. But you need a reference for that. You need to know I'm measuring time, the passing of time, but based on what? Maybe you started measuring at noon in Lisboa, so that you know what time it was throughout your travel. And then there was mechanical clocks that started getting more precise, smaller. Same thing again, they're measuring in quartz and atomic. I mean, like in your computer, you've got a device that can give you how many ticks have gone by. But if you don't have a reference to which you can say, if I ask my computer, how much time has gone by, he's going to go, oh yeah, it's like 5,360,000 ticks. He'd be like, yeah, great. I mean, that's not useful for me. I need to reference that chronometer to something else. Which leads us to clocks. Clocks and all chronometers need to measure time in a monotonic fashion. If I've got a clock that starts changing rate, it's not going to be really that useful. Sorry. And the absolute value of that clock is not useful per se. If I look at my watch, I mean, my watch doesn't say, oh, this spring is at this position. No, I'm going to be taking my clock, and then based on a reference, tower clock or NTP, I'm going to go, okay, now it's noon. So that at any other point during the day, I'll be able to go, the clock will tell me, oh, it's this much time past noon, for example. Right. So that's essentially what time is. And also the one thing which I haven't mentioned in that is that if we want to be able to synchronize events, we want to have, let's say, something simple. We want to have a meeting at a certain date and time. We need to have two things that are identical. We need to have the same reference of time. That's to say, both our watches need to be tuned. I mean, we need to take our watch and we need to make sure that noon is actually noon based on some reference. And also, those watches need to be going at the same rate, because otherwise, if my watch runs slower, I will arrive at the meeting 10 minutes late for you, but I actually arrived on time. So clocks need to have the same rate, and we need to have some identical reference point in order to be able to do synchronization, arrive at a certain event or time, or say that a certain event happened at the same time for everybody. So, enter GStreamer, because after all, it's the GStreamer conference. In GStreamer, the first thing that we're going to be using for time is GST clock. It's an API with some base implementation, actually various implementations. It has one simple requirement, is that it's to report a monotonically increasing value. If I get the time on that clock at a regular interval, the difference between the values that it returns must be constant. So it has an API, GST clock get time. And it'll give me an absolute time. 5 million ticks, or if I'm using an audio clock, it'll give me, it's God knows how many samples since you started the sound card, something like that. And then the other API that we have in GStreamer for the clocks is to be able to, along with the clock, be able to say, wait until this absolute time on your clock, synchronously or asynchronously. All of that works without a pipeline. You don't need a pipeline to use a GStreamer clock. So, where do we go from here? I needed to shorten this talk. There are plenty of different implementations. It doesn't matter for the rest of this talk. Just assume that I'm using a unique POSIX monotonic clock. The one that doesn't go forward or backwards. It returns to me a monotonically increasing value. Jan will give a talk this afternoon about distributed clocks also. He'll give you a bit more details of how you can go further with that. Anyway, my first awesome graph. This is the values that the clock can return. And there's no starting point, it's just, I can just query, do I have a pointer with this? No. Yeah, here we go. As the real time, universal time goes by, I can then go like, oh, what's the current value? Oh, what's the current value? Oh, what's the current value? And so forth. All that matters is essentially that between a certain moment in time, I mean, if I query the clock at 2 different intervals, I'll then be able to use that difference to go so much time has gone by. A tiny bit on GStreamer. I'm going to take a very simple example. Video test source, time overlay, XV image sync. Essentially, an element which generates some video buffers, which will have timestamps on it that increase. And then to make it a bit more visual, I'll pass it to an element that overlays the time on it, the buffer timestamps, for now. It's not actually accurate. And then afterwards send it to an element. The only job of the element is just to show it on the screen. Is to have some visual feedback. And I'm going to deactivate the synchronization system. So there we go. So boom. Can you see it? You can see it. Anyway. Now, what happens? What you're seeing at the top is hours, minutes, seconds, and milliseconds. Even though those buffers have timestamps on it, it's actually going full blast. Essentially, this is working like a Unix, like Unix pipes. I've got a process that produces video buffers, a process that does an operation on it, and a process that displays it on the screen. So, oops, where are we going? There we go. And so the buffers had, I'm not showing it, but trust me, the buffers have got timestamps on it saying, oh, 0 30ths of a second, 2 30ths, 3 30ths, buffer timestamps. How, from that information, we're going to end up synchronizing them so that they do appear, if I enable the synchronization, so that they actually get displayed in such a way, synchronized. Oops, here we go. What's our goal? For each buffer, we want them to be displayed at a certain time after we start playing. We're going to need to know, so there's 2 parts to that. It's so many seconds after we start playing. Those so many seconds being, let's say, the buffer timestamps for now. In order to know after we start playing, it's a delta, it's a time difference. So we're going to need to know a reference point. That's going to be what we're going to call in GStreamer a base time, the moment at which we switch to playing, and so many seconds after. And that's going to be what we call the running time, the amount of time that we have been running or playing. What does it all look like? So we start, so that's our GStreamer clock absolute time. The moment we switch to playing, we get that clock value. And we're going to use that to determine some running time, the amount of time that we have been in playing. So obviously at the beginning it's 0, and then it increases. How are we going to use that to do our synchronization, decide what is the clock time at which I'm going to be displaying that buffer? We could just go, yeah, great, I mean, our buffers start with 0 and then 1 30th of a second, 2 30ths of a second, and so forth. We could just use that and go take, for buffer timestamp 0, you're going to be synchronizing it at running time 0. That could work. But what if it's not, the buffer timestamps don't start with 0? Let's say I'm seeking in a file. I'm seeking 2 hours into my movie. The buffer timestamp are going to start with 2 hours. Do I wait for running time 2 hours? Do I wait for my pipeline to have the clock to have gone through 2 hours before it starts synchronizing and displaying? No, I actually want it to start displaying straight away. So we need a reference. Sorry. From which we can calculate the running time at which that buffer should be displayed. And so for that, we need more than just buffer timestamps. We need more than just a base time and a clock. We need to bring in more context to our buffer timestamps. And that's all that information of bringing in more context of what are we going to be doing with our buffer timestamps is all put into the GStreamer segment and the associated segment event. So it's going to help us define all of that. The first 2 values that we're going to start caring about in segment are going to be start and stop. They are going to tell us essentially what are the first and last valid buffer timestamp in that stream. Our reference point, if you want, for buffer timestamps. So if we take any buffer, we take the timestamp of that buffer, and we subtract the segment start from that, and that will give us the buffer running time. It's not the end. This is just to introduce step by step. So, there we go. For any buffer, in the initial example, I mean in the most basic example, the buffers will be coming out 0, a 30th of a second, 2 30ths, and so forth. The segment start will be 0. That's fine. So 0 minus 0, running time 0, start synchronizing it straight after we switch to playing. A 30th of a second minus 0, 1/30th after we've switched to playing, and so forth. But in the case where you were seeking to 2 hours into your movie, you'd end up with the buffers timestamps would be starting from 2 hours, but the segment start would be 2 hours, and therefore that first buffer would end up 2 hours minus 2 hours, running time 0. I want you to start displaying it straight away, and so forth. 2 hours plus 1 second, minus 2 hours, 1 second, and so forth. Right. Moving on. The first question we're going to ask ourselves is like, okay, so this is great. I mean, I'm doing my synchronization, and it's the amount of time I started playing. But what if I pause? And if I'm 5 seconds in, oops, where's my pointer? Let's say I'm 5 seconds in, I pause, wait 10 seconds, and then resume. So I pause at this absolute clock time, wait for 10 seconds, and then resume. Well, that timestamp, that buffer would be arriving too late. So what we do is actually, the running time is going to be the amount of time we spend in playing. So when we go from playing to pause, we're essentially going to go, oh, how much time have we spent in playing? Remember that. And then when we go back to playing, we're going to get back the clock time, subtract the amount of time we've spent in playing previously, and that will give us the corrected clock running time to which to synchronize. Moving on. Great. So what happens if I want to play faster or slower? We have several solutions. So let's say I want to play this video test source pipeline 2 times faster. I want it to essentially synchronize buffers faster. The difference between each buffer running time, should be smaller. I could, in the element, go, okay, let's modify my timestamps. But we could avoid that, because in the end, there's just a simple formula that helps us define. There is a simple, we can just delegate that to elements that actually want to do synchronization. So what we're going to do is that we're going to add in segment rate. There's in segment, there's a field called rate, which essentially tells you this stream, you should synchronize it this much faster. And it has also different directions, forward, backwards, playback. And we're going to adjust the running time, the moment at which that buffer should be rendered or synchronized. Quite simply by dividing it by the rate. So this part, here we go. This part is what we saw just before. So I figure out the running time. But if there's a rate, if I want to play it faster or slower, I'm going to divide or multiply the moment at which we're going to be synchronizing. Which essentially ends up in something like this. If we're playing at, I don't know, let's say we're playing at 2 times the rate here, the running time in the end, the moment at which I want to do rendering or synchronization, will take the difference, the running time, the difference between the buffer timestamp and the segment start, and then divide it by the rate. So divided by 2 in this case, if it's, I want it to play faster, and so it'll be synchronized faster. If it was slower, let's just say the rate was between 0 and 1, then that division would end up increasing the running time. So we'd end up synchronizing them later. Okay. What if I want to play backwards? In this case, the buffers are going to be pushed out with timestamps decreasing. I'm assuming it's coming from the output of a decoder or from video test source. But essentially, the buffers that are coming out have got their timestamps decreasing. So at this point, if I want to figure out when I want to synchronize them, I do want to, still the same idea is that I want to synchronize them so much time after we have switched to playing, that running time. Except that since we're starting from the end, we're going in reverse. This time we're going to be using the segment stop value, which is essentially saying, from this point, from the stop position, I want you to synchronize it. How can I say? Let me get this right. We are starting from that stop position. So if the first buffer to render is the same value as the segment stop, then the difference is 0. It's going to be, the running time will be 0, and it's to be synchronized straight away. So it's only a very slight difference, and this is why people sometimes wonder, what does segment stop? Why is segment stop useful? Well, it's sorry, it's useful to do this kind of reverse reverse playback. So it ends up being woohoo. So remember, the buffers come out in this order, in reverse. So like, boom, boom. So this is the first buffer, second buffer, third buffer. So we measure this difference between the segment stop and that buffer timestamp, and then that's going to give us that interval. Okay, it's not really the right scale, but anyway. This interval is bigger. It ends up being synchronized later, and so forth. Same thing again. Right. And then afterwards, if there was the rate, if it wasn't minus 1.0, but if it was minus 2.0, then that interval would be decreased, and we'd be synchronizing faster, but in reverse. Okay, so far so good. The last item, which is confusing for a lot of people, is stream time. What is stream time? So stream time is the user-facing time. That is to say, when you do seeks, when you query for the position in a pipeline, that is going to be stream time. It's what you're reporting to the user. It's what you'll display in your seek bar or in your position reporting. It's confusing because most of the time it's the same value as buffer timestamps. If you use files, like a 2R file, I think virtually all container formats, the timestamp for the first buffer is 0. And yes, your position in the stream is also 0 for that buffer. So it's a bit confusing. There are use cases where the timestamps on those buffers are not the same as what you're trying to, what is meaningful for the user. RTP timestamps, DVB timestamps, when you start watching a stream, the timestamps can start from any random value. You don't want to display that to the user. You want to display something more meaningful. An example is if you connect to a live RTP, RTSP session, a presentation that started 30 minutes before, because you hadn't checked your clock and you arrived late. Anyway, you don't care about the RTB timestamps. They can be anything. On the other hand, it would be nice if in your player, it would show you, oh, you're 30 minutes into the presentation, and the time carries on, I guess it goes along accordingly. Once again, we're going to need some kind of reference to be able to correlate the buffer timestamps to the stream time. And that reference is the segment time. So essentially, in the same way that we use this reference to calculate running times of buffers, this time we're going to be using the segment time for each buffer will take subtract the segment time to figure out the stream time of that buffer. Right. And we've essentially shown most of this summarizes pretty much. There are some other fields in segments, like the base field, but if at least this is clear for everybody and the relationships between everything is clear, that should make it much easier to understand the other synchronization concepts in GStreamer. So remember, these are really the four things to remember, is that the clock can be any value. I don't care how my clock is implemented. As long as it's monotonically increasing, I can then start going, the pipeline can get a base time, which will serve as a reference for the running time of the clock, and to determine, to then go for a certain buffer, I can then use segment start, segment stop, and the rate to figure out a running time, at which I'll start doing synchronization. And then in some rare cases, the user-facing time, the stream time, will be different. And that is also very important, something to remember when you do seeks, when you do position queries. It's the stream time that you're using. Right. Okay, let's move on. So we've been talking about using, how do we determine for a certain buffer when we're going to figuring out the synchronization time. But we can also use clocks to figure out when an event happened. In the same way that in real life we can schedule an event, we can also know, oh yeah, we had beer yesterday evening at this time, if you can remember. So in GStreamer we're going to be doing the same thing for when doing capture. When we're going to do live capture, so live event is kind of special. It's something that in GStreamer, when we say a live source, it is an element which cannot, in order to capture that frame, that buffer, whatever, from outside of GStreamer, we need to do it at that moment in time. We can't do it before. That video frame hasn't, it hasn't arrived yet, and we can't do it later because we will have missed it. That event will have will have happened and gone. More realistically, if I'm doing video conferencing, if I'm using my webcam and my microphone and it's capturing me, when the camera is grabbing those frames, what it is grabbing did not happen before or after, it's happening at that moment in time. Same thing for the microphone. And what do we want to do? We want to make sure that those buffers corresponding to what we captured from the microphone and the webcam end up with timestamps and running times corresponding to the same moment in the real world, for the real event. So this is what I call a real-world event outside of GStreamer. So I'm recording myself, I clap my hands, and I want to make sure that the sound of my clap, recorded by the microphone, ends up with the same buffer timestamp and running time as when the camera got my two hands like this. Only problem, there is going to be a latency between the moment that action happens, the microphone converts it to digital, does the analog-digital conversion, and finally gives me the chunks of audio segment corresponding to that moment in time. Likewise, for the webcam, there's going to be a delay between the moment it starts capturing and it finally gives me that, that video frame. So we're going to end up in that situation where when we finally get the corresponding audio and video data, we actually get two different clock times. So how do we end up, but we want them to have the same buffer timestamp. We want to have them correspond to the same moment in time. So what do? We could just go, okay, I know the delay of my capture device, audio, video capture device. I could just subtract that, that delay from the moment I finally receive this audio sample or video sample, so that it ends up being the same buffer time. I've managed what I wanted. I mean, then if I capture it to a file, I mean, if I encode it, capture it to a file, and then I play back that file, it'll be in sync. But there's a slight problem, is that if we do that, and, oops, let's go back a second. If I do that, I'm going to end up with the running time, the moment at which, if I wanted to capture some video, do a video effect, and then show it on my screen, I would end up with a running time which is in the past. So when it reaches my video display, the video sync, it'll essentially go, ah, it's too late, go away. So we haven't really solved the problem. The thing is that we need to introduce a new concept, which is latency. I need you to delay the whole synchronization in such a way that downstream it will not arrive too late so that synchronization can happen. But there's actually another challenge. We don't want to have that delay be massive, because otherwise it's really easy. I mean, otherwise you just go like, oh yeah, just put in a latency of 10 seconds and everything will arrive on time. Well, actually no, because 10 seconds is not going to be great. I want it to happen with the lowest delay possible, but enough for all the processing in the pipeline to happen. So how are we going to figure that out? Sorry. All the elements in the pipeline, hopefully, can report how much latency they're going to be introducing. That's to say, the minimum delay in running time, so in clock corresponding time, that they need in order to produce or to process some data. So in the case of our webcam, we're going to have a certain delay. For our audio source, we're going to have another kind of delay. For decoders, we might also have some other delay, especially if you've got, if you've got reordered frame, you'll need to wait for the following frame, or maybe two other frames, before you can start outputting the decoded result. And we're also going to ask, what is the maximum latency you can support? That one is a bit hard for some people to grasp, but if you've got an audio ring buffer in your audio source, and so essentially you've got the sound card is writing into that ring buffer, and then GStreamer, we're reading from that ring buffer, we're pushing out buffers into the pipeline. If you, the maximum latency is essentially that they're kind of racing along, and if you don't read out the data fast enough from the ring buffer, you might end up in a case where the sound card will be overwriting data which you haven't pulled out yet of the ring buffer. You will have lost that data. That is essentially what the maximum latency is. So maximum delay that that element can support. So essentially the pipeline queries all elements in the pipeline. Every pipeline reports this is the minimum and maximum that I will introduce and can support. And we end up with something like this. So those black lines are the ones that we talked about earlier on. So the audio source goes, oh, the minimum latency I will introduce is this much, and the maximum latency I can support is the ring buffer size in this case. Same thing for video. And once the pipeline has got all that information, it'll figure out what is the minimum delay that I need to introduce in order to give all elements in the pipeline, all processing in the pipeline, a chance to be synchronized in time. And it just grabs the maximum or all minimum latencies reported. This is cumulative, by the way. So if there is, for example, I don't know, some other element after the video source that introduces delay, it'll increase that minimum latency. Figure out all of that. We also figure out the minimum of maximum latencies that the pipeline can support. That is some sanity check. It's so that, imagine the case where your video capture, so for video capture, minimum latency, maximum latency, but the audio source was configured in such a way that that is the minimum latency, but the maximum latency and the rig buffer size is too small. It would end up being up to here. Then we would have a problem, because in order for the minimum amount of delay that we need to put in, latency, for video frames to be displayed in time, would be greater than the maximum amount of delay latency that the ring buffer needs, that the audio source needs. So the rendering time changes slightly, the synchronization. We're no longer just synchronizing against, okay, let's figure out the running time for that buffer, and then I synchronize it against this clock running time. We will actually need to add that latency, which ends up being, so we did modify the running time of the buffers because they do correspond to the same event in time. But when we do the synchronization, we will delay the synchronization by the pipeline latency. So yeah, other elements can introduce latency, decoders I mentioned, some transformation element if you do some, if you use audio resample, for example, and you want to use some high quality resampling systems, it will introduce a latency of a few samples, so it can report that properly. And then you can also, if you end up in the situation that I mentioned earlier on, where your ring buffer is too small, so the maximum latency is lower than the minimum latency of your video source, well, you can actually increase that maximum latency by just adding queues. Queues will be able to buffer up more data, and it'll avoid you losing it. I have no more time for more details. There are plenty of other things in GStreamer that we could talk about. Different clocks, how the different clocks behave, how you can do clock slaving, remote clocks. Interesting challenges that we have right now. For example, RTP and DVB, they need to figure out what is the remote clock, at what rate is the remote sender sending us data. So we need to estimate that rate to end up with the same rate of playback. That we're doing the modification in those elements. So we're re-timestamping. Ideally, we shouldn't do that. We should just go, oh, here are the timestamps, and by the way, the rate should be changed by this much. But Jan will be going a bit over some remote clocks and so forth. But hopefully, it is clearer now what running timestamps, the various time domains, stream times, running time, buffer times, clock absolute times, how the segment handles those references. Yeah, hopefully you've got all the basics. Everything else in GStreamer is easy. I'm kidding. That was the easy part. And that's it. Are there any questions? Oh. Thank you, Tim.
Hi. So based on what you said, is it a bad idea to put completely unrelated sources in the same GST pipeline? So, for example, you have 10 different people in different video conferences in the same GST pipeline, potentially having different latencies and that kind of thing for synchronization.
Well, so essentially having different sources which have got different latencies and
like unrelated that you don't need to synchronize together. So you would want to maybe synchronize audio and video on a few of them, but not all the things in a GST pipeline.
Right, and those might be coming from. I imagine you're talking about cases of live streams remote RTP participants? Or?
Yeah, exactly. So,
right. Yeah. Well, so if you've got those two, associated audio-video streams from one participant, normally they should have the same NTP. They should have already some kind of correlation. So you will be able to then end up, yes, those elements, those two streams, you can synchronize them together, but then another participant might have a different rate, might have a different network latency, and so forth. You can have them.
Edward,
yeah.
in the pipeline, there is a signal that you can override, and then you aggregate latency separately, so it moves up sync for each participant. Is this that last one?
But that is the remote latency, not the local pipeline.
You can aggregate. So it's aggregated by GStreamer, but you can override that algorithm with one that's separate. There's an example from one on the internet.
So the answer is there's an example on the internet. I'm sorry, I haven't quite grasped the question. Any other questions?
So before they talked about the problem on calculating the latency with decoders that reorders frames. So it's something that can be changing dynamically, or it's only calculated on the state changes?
Okay. So yes, I was just assuming there that I was just showing the logic of latency calculation, and I just mentioned that and then the pipeline at a magical moment goes let's query the latency and minimum maximum. Elements can actually, if they have latency that can change throughout the course of playback, can then emit a latency message on the pipeline, and which essentially says it's changing. You need to recall it, and we need to recalculate the latency, and the application should then go, oh, latency message, I need to requery the latency on the pipeline, and then it'll be applied. It's a bit tricky changing latency for obvious reasons, because all of a sudden you're shifting all the synchronization. So there might be some glitches, but then in some use cases it is interesting, because then you end up having a more optimal latency. I can delay it less, interesting for RTC, or I need to delay it more, because otherwise everything will be dropped.
Thanks.
It should be possible to do it without the glitches. We just don't implement that yet.
We should be able to smooth that delay, having smarter switching from one latency to another, or from one rate to another, with some smoothing. It's just that right now.
There is a tentative code that does that in one bug.
There's code somewhere, apparently.
So there
was
in
one more question somewhere here.
How do you handle sub-pipelines with different rates when they come together? So you have a local audio source, like alpha source, and then you have a network source from a stream, and you mix that, and then send it to sync, right? And the network stream has maybe a slightly faster or slower rate.
Okay. That is what I mentioned in the very last slide of there are cases where, so for remote live especially, you need to figure out that remote rate. Here I was assuming that the whole pipeline and everything is using the same rate. Right now, you would need to do some retime stamping to conform one stream to the other, so that they end up with the same running time. And that's what DBB does. That's what the TSD Mark Server for live streams does. That's what RTP jitter buffer does. But ideally, we should be able to do some estimation so that you just send some information. This clock is slightly faster. The running time, you need to shift it by that much, so that then afterwards you can synchronize properly in adder based on running time. And then it'll also send the information to your network clock, to your network sync, you should actually synchronize slightly faster, slightly slower with that shift. We will still come back to the concept of it needs to have coherent running times.
This may be a question better suited to James' talk. I'm not sure. Please tell me if it is. Is there any accepted best practice in dealing with hardware decoders where you've got a hardware-based reference clock?
With?
Hardware decoders where you've got a hardware reference clock. So an STC running in the hardware and you're decoding you've got a transport stream, a DVB.
The whole, I mean, I didn't mention nature. I mean, it doesn't change the nature of the synchronization, whether it's local, remote, I mean, hardware accelerated or software. The challenge is really figuring out, and assuming you mean for latency or for just synchronization?
Just for synchronization.
Oh, yeah, that's an interesting one. So yeah, one of the challenges of supporting hardware accelerated decoders, encoders, whatever, is that most of the time they don't provide an API by which we can correlate an encoded frame to the, if it's a decoder, for example. That encoded frame produced this decoded frame. So that then afterwards we can correlate information about it like buffer timestamps. If your system does not have that, you're screwed. You can only guess. I mean, then afterwards you can do guesses like, yeah, maybe that corresponds to that presentation timestamp, maybe or not, or yeah, I'm sure Freescale has got some interesting.
Linux actually has timestamps, and there is a flag somewhere, I think, that the driver can set and say, I'm copying timestamps for man-to-man devices. So you can put the input timestamp or something there, and this when entering the encoded buffer or whatever, and get the same timestamp on the output.
Right.
Although it's not nice because it's time biased, I think, so the old stuff which ran around in
Yeah.
2038 or whatever.
But from a GStreamer point of view, it doesn't matter. I mean, as long as we have a reference, it doesn't need to be actual timestamps or whatever. It could just be a counter, a frame counter, or something like that. As long as we can correlate for hardware components, you know, this input corresponds to this output, then it's fine because we can carry over metadata, including timestamps and so forth. And I think this should be the last comment.
Yes, we should break for lunch after that.
Yeah, that's definitely an issue, and especially, I mean, the Linux API is there, but the hardware sometimes, you trick the hardware and try to figure out which is which in the driver, but it's not nice either.
Yeah, the VPU, the Freescale VPU is like, woo, yeah, I'll give you something. Anyway, thank you very much. It's time for lunch. And